Behind me is the entrance to the JET tokamak, which is currently the world's largest fusion reactor. It routinely makes plasmas of more than 100 million degrees, 5 times hotter than the centre of the sun, and today is the hottest place in our solar system.
A global industrial revolution is underway.
Yes, we have a technological challenge for our environment, for the well-being of the population of the planet, for civilization.
Driven by passionate, dedicated individuals intent on shaping a new world.
I do it because I look at my kids, and I honestly am convinced that this is the way.
A cleaner world.
There is a way forward other than burning fossil fuels out of our funnels.
A greener world.
This wind farm is producing more hours of power into the grid than all wind farms in the UK and probably in the world.
What we've done in the past is not going to solve these challenges. We need to find new ways, and I think the only way to do that is to bravely step forward and implement technology.
Together, they are pushing engineering to its limits to create extraordinary machines that can protect our planet for the future. It may be the greatest technological challenge ever undertaken by humankind. The quest to produce the ultimate energy solution, a reliable source of clean power.
Windmills are great, solar is great, but they don't work when the wind's not blowing or the sun's not shining.
So what if we could create here on Earth our very own version of a star? A machine that makes power from nuclear fusion.
When fusion is working, it will allow us to have baseload electricity, replacing all coal gas stations without producing any greenhouse gas emission. The potential for fusion is massive.
So fusion offers humanity an unlimited source of energy.
But there are big challenges. Most of those challenges are actually engineering challenges.
It has taken 70 years and a truly global effort, which has seen science transcend the boundaries of Cold War politics in a common goal. But so immense are the challenges, the goal of a power-producing fusion reactor has so far remained elusive and out of reach. It's going to require the mastery of extraordinary temperatures, the creation of magnetic fields eclipsing anything that has gone before, and the ability to sustain both for long periods of time.
For me, in terms of the world's energy needs, it's not a matter of if, but a matter of when for fusion.
For years, the attention of thousands of scientists and engineers across the globe has been fixed on crucial tests being conducted at this former military airbase in the UK. The research being carried out here is pushing the boundaries of the science and technology that underpins the whole concept of a fusion reactor. If successful, it has the potential to change the world.
Every day is a daily challenge, and we are doing first of a kind all the while. So every day is an exciting adventure on the way to a very important goal for the whole of humanity.
But these tests are just part of a much bigger story. For over a decade here in Provence, France, an immense construction project has been underway. It's here, over a few short months, that pieces of the most complex technological jigsaw ever created will be assembled, costing $22 billion. It'll be the most expensive scientific experiment in the history of mankind. Its name, ITER, the International Thermonuclear Experimental Reactor. Nothing of this size and scale has ever been attempted before. The 42-hectare platform is 400 meters wide and covers an area comparable to 60 football fields. If successful, it will form a new blueprint for the world's future energy production. A giant machine that makes use of a process at the subatomic scale, a process which provides the energy for the building blocks of life, fusion.
Everything that we see here is a result of a supernova of an ancient star, and that ancient star in that supernova process occurred by the fusion reaction. So as a scientist, I think it's fantastic because we're developing and controlling the very essence of the building blocks of nature.
If you could get close enough to the sun to peer inside its core, you'd see atoms of hydrogen joining together or fusing, releasing huge amounts of energy in the process. The source of energy within an atom comes from what holds it together. It's known as binding energy. So if you want to break one apart, you need a lot of energy to do it.
In the sun, because you have this enormous gravitational field, the hydrogen that's in the sun is compressed to very high pressures and temperatures to the point where when they collide, there's a significant probability that they'll fuse, they'll stick together. They stick together in pairs until you get helium. The helium has slightly less binding energy than the hydrogen did to begin with, and that difference in energy is released. It's released as heat and energy of the products and as light that we see from the sun or the stars.
Every second, the sun consumes about 600 million tons of hydrogen, releasing 500,000 times more energy than is consumed on Earth in an entire year.
The sun works because it's so big, but it's incredibly inefficient. A meter cubed of the sun actually only produces 30 watts of energy of heat. You and I actually produce more heat than the sun does per cubic meter. So the sun only works because it's absolutely enormous.
Harnessing the power of nuclear fusion has often been referred to as bottling a star. But in reality, our version of fusion will need to far exceed what a star can do.
The sun uses the lightest element known, hydrogen, to fuse together. If we actually use slightly heavier versions of hydrogen called deuterium and tritium, we can make that process happen much more quickly, much more effectively, and that is the process that we plan to use on Earth to actually recreate those fusion reactions. It's a good job the sun doesn't use those fuels, because if it did, it would have burned out in less than 1 second, rather than the 5 to 10 billion years lifetime that the sun actually has.
Fusion is all about creating a superheated, electrically charged gas known as plasma. To achieve this, you need 3 things: temperature, time, and containment, all of which create huge challenges. Firstly, how do you create temperatures of over 100 million degrees? Secondly, how do you keep the charged nuclei together long enough for them to fuse? And lastly, once you have achieved the first 2 and created plasma, how do you contain a substance that would instantly vaporize any known material it touched? The teams here at Culham and in France believe the solution lies in a concept first conceived of in the Soviet Union in the 1950s, a tokamak reactor.
So this is JET. This is the Joint European Torus. It's a tokamak. It's a device that uses a magnetic field to confine a plasma at very high temperatures in order to make nuclear fusion. there's a system of magnets on JET, one system wound around the torus this way and one system wound around the torus that way, that keeps the plasma in the center of the vacuum system away from the walls and allows you to raise its temperature to this 100 or 200 million degrees C. It's donut-shaped, it's toroidal, because the magnetic field confines the plasma from moving across it, but it has no confinement properties along the magnetic field. So you can't have ends in the field, and the way you avoid having ends is you twist the magnetic chamber into a torus. If you go anywhere in the world and you look at magnetic confinement devices, you'll see different kinds of donuts. This one's called a tokamak. JET is a high vacuum system, which we pump out at the start of every experiment, and then we inject a small amount of gas into the chamber of deuterium and tritium, which are the two isotopes of hydrogen we use to make fusion. These are then ionized using a very high electric field that is generated around the tokamak. Once they're ionized, they conduct electricity, and the currents inside there are up to about 4 million amps. At those very high currents, you heat the gas and turn it into a plasma.
So we've electrically charged and heated the gas to create plasma. But at this stage, it's a mere 10 million degrees Celsius, which might work for the sun, but without the benefits of the sun's size and gravitational field, it's just a tenth of the temperature needed to create energy-producing fusion here on Earth.
So what do? We add additional heat systems for heating the plasma, for boosting the temperature of the plasma by another factor of 10 or so. There are two such additional heating systems on JET. One is a resonance system, a bit like a microwave heating food in your kitchen. This system inside JET is capable of putting 8 to 10 million watts of power into the plasma.
To give you some comparison, that's something like 10,000 times the power of a typical microwave oven.
The second additional heating system is this large system here, where we inject very high energy neutral atoms into the plasma. Neutral, so they don't see the magnetic field. This system and its sister on the other side of the machine are capable of putting more than 30 million watts into JET. The combination of the two heating systems lets us boost the temperature up to those we need in order to make fusion.
But the problem is that as large and sophisticated as JET is, creating the plasma requires so much power that the reactor doesn't actually generate more power than is put into it. Scientists often compare it to lighting a fire. You need a match to get it started, but ultimately you need that fire to keep itself going. The problem is to create enough plasma to keep the temperature up, which is what is called burning plasma. And that's where ITER comes in.
So ITER is the next step. And so we're building off of all the knowledge of these existing machines to be able to go the next step, and where we put, for every 1 watt we put in, we would be able to pull out 10 watts from this fusion reaction.
This has never been done before. We have excellent calculations that have been validated by experiments at the level we can do them now, but nobody's gone to the level that ITER and a future power plant for fusion would have to go to, which is dominant self-heating. And so that's one of the really big physics challenges that's exciting, is this will be the first time we go to the place where we have a true burning plasma.
And that burning plasma can be used to heat water flowing through pipes, which in turn can be used to power turbines, just like in a conventional power station. Just 250 kilos of deuterium and tritium could power 1 million homes for a year. To do the same thing, a coal-burning power station would require 2.7 million tons of coal. But while deuterium is readily abundant and can be distilled from seawater, tritium, a vital part of this technological jigsaw, is a different matter.
Deuterium and tritium are two different kinds of hydrogen. Hydrogen is the first element in the series in the elemental table. but it comes in 3 different flavors. Protium, which is the one that is normal. More than 99% of the hydrogen on Earth is protium. Deuterium, or heavy hydrogen, and tritium, which is heavier again. Tritium is radioactive. It decays with a half-life of a little over 10 years, so there isn't very much on Earth.
In fact, the total world stockpile of tritium is only around 20 kilograms, mostly produced by reprocessing spent nuclear fuel from conventional fission reactors.
So the way we get around that is we're going to make our own tritium. We're going to put lithium into the blanket of a fusion reactor. The neutrons that are produced by the fusion split the lithium and make tritium. In that way, we make more tritium than we burn. We feed the tritium we've made back into the reactor, and we have something that's effectively using deuterium and the lithium as a fuel. Lithium you can mine. It's available on Earth in deposits. There's also lithium in seawater. Because the deuterium and the lithium could potentially come from the seawater, everyone has access to it.
This potential for a reactor to effectively produce its own fuel from such an abundant source is just one more reason why ITER is so important. When completed, it will be the biggest fusion reactor ever constructed. Weighing 23,000 tons, it will be 3 times heavier than the Eiffel Tower. And then there's the magnets, vital for containing the burning plasma and keeping its immense heat away from the vessel walls. Each one of its 18 toroidal magnetic field coils will weigh the same as a fully loaded Boeing 747. Together with another 6 circular magnets, 48 meters wide and weighing up to 400 tons, they will exert a force equivalent to twice the thrust of the space shuttle at takeoff. And all of this in the quest to produce and control large amounts of plasma.
Hydrogen, when it gets ionized into a plasma, it's got a beautiful pink glow to it. So you have this sort of pink aura you feel like you're making a work of art and a work of science at the same time.
To create the very powerful electromagnetic fields needed to confine the plasma, ITER's magnets are like nothing ever produced before. It's a process that started 30 years ago. And heading the magnets division is Neil Mitchell, a man who's been involved in their development from the very start.
It's quite personal because, I mean, I've spent not only my career, but my life on this project. It's very satisfying to think, oh yeah, we were sketching that on pieces of paper 25 years ago, and look, it looks what it looks like. Yes, I mean, it's amazing in the last, well, particularly this year, actually, because really this year, everything is arriving on site.
The type of electromagnets Neil and his team are using are known as superconductors. These operate at incredibly low temperatures where the wires in them have no electrical resistance, meaning that once charged, the only power the magnet consumes is that needed to keep it cool.
The magnet system of ITER has got quite a lot of energy stored in it. It's around 40 gigajoules. If a gigajoule makes any sense to you, it probably doesn't. It'll certainly run several kilowatts of power for a day or 2 or 3. There's a lot of energy in the magnets, but it's not being consumed. You put it in and it's stored, and the currents just circulate forever for free.
1 gigajoule represents the capacity of about 4 long-range electric cars. So the magnet system within ITER stores the equivalent of about 160 fully charged vehicles. But who would make these extraordinary devices? Before ITER, the total global production of superconductors was only 20 tons a year. ITER's magnet system will weigh almost 10,000 tons.
The superconducting magnets for ITER are particularly challenging. I've been working 30 years in the superconducting magnet industry across the world, but I have to say the ITER magnets are by far the most complex I've been working on.
But it's not just their complexity. Their sheer size meant that those companies that did produce them wouldn't be able to transport them on existing roads.
So you need to have a factory very close to the sea.
Which is easier said than done. For CIMIC in Italy, in order to secure the ideal location, they had to take over premises already occupied by a company producing dishwashing machines.
But in the deal, there was the agreement that they had to absorb, to take on board most of the old workforce.
Now the workers are at the cutting edge of a technology that has multiple applications from CT scanners to maglev high-speed railways.
They trained first these people and then started working together. And I have to say that after 2 years, I have a team of very motivated and skilled technicians. I think a very important factor is the motivation. And I think to participate to a project for which the final goal is to produce clean and renewable energy and hopefully save the future of the planet, I think this is part of the reason why they were able to so quickly to bring up to speed these people.
Each of the 18 toroidal magnets contains almost 5 kilometers of conduction coil, each themselves containing 1,400 superconducting niobium, tin and copper strands. It has to be wound into a spiral with an accuracy akin to the thickness of a human hair. 15 kilometers of robot-controlled welding seals it into a casing. Wrapped, insulated, then vacuum-sealed in resin, these magnets also contain cooling pipes through which liquid helium will flow. The magnets will need to be kept cold for years at a time, and the temperature that will be required is minus 269 degrees Celsius, just 4 degrees above absolute zero, the lowest temperature physically possible. When the reactor is operational, in the center it will be the hottest place in the solar system. And just a few feet away, it will be 2 degrees above the lowest temperature in the universe, which occurs in the Boomerang Nebula some 5,000 light-years away. To attain such low temperatures is beyond any existing capacity. So they're having to construct the world's largest helium refrigeration unit. But to keep the cold from dissipating, the scientists then needed to find a way of insulating the reactor. The answer? A giant vacuum flask built from 3 enormous stainless steel sections known as a cryostat.
So we are now in the cryostat workshop. And so what you see here is the workshop where we are building the largest fridge ever constructed. So we are now entering, sort of crawling, mind your head, it says, into the cryostat, the upper cylinder. And it's here where you can feel, see and sense the dimension of our machine. It's going to be 30 meters wide, 30 meters high. This is just the upper third. And yeah, it's going to be a big beast.
It's easy to look at the challenges that ITER faces and assume they're all to do with science and engineering. But this project involves 35 different nations, representing over half of the world's population. On such a long-term project, governments will come and go. So how do you ensure that new leaders, often with a very different agenda and ideas on what they should be investing their money in, remain committed to the fusion dream? It has been estimated one giant company doing all this by itself could get things done a lot quicker. But that misses the point of what all this is about, giving everyone a vested interest.
Why do we have 35 nations? You know, we always keep saying ITER has two main goals. One is to build this machine, ITER, and to prove that, yes, we can do fusion, we can generate energy by fusing atoms. This is the main one goal. But at the same time, we have all these nations on board, so we are building up, developing a fusion industry around the world.
So ITER is really the focus point of all of this research pointing to one machine, ITER, and then from that one machine, all the countries can go off and build their independent machines.
The person charged with coordinating the production of all these different components is Colette Ricketts, who previously spent 18 years working as a physicist with the team at Cullum.
So for me, the hardest thing on this project, with millions of components coming from literally across the globe, the challenge is always about how do we communicate. Can you imagine on a schedule that's 250,000 activities and milestones, how many issues are faced every day? Every day. Of all of that, what's key? What matters? And then to pick 5 things, 15 things, absolute maximum, to share with the project and say, we have to solve that problem. Simplifying what is effectively the world's largest, most complicated construction project today into human, understandable elements. But I have no doubt the people here can solve whatever is thrown at them. They really know their stuff.
In an environment where so many different people from around the world, speaking numerous different languages, are working together to push the boundaries of science, one thing in particular has turned out to be of surprising importance in helping communication: the canteen.
The idea of just sitting down to eat, just gently getting on with conversation, which is exactly how the languages were designed to be used. They were never designed to be used in the classroom. They were designed to be picked up gradually by people saying, can you pass me that? Can you pass me that? I like this. Using the same simple phrases over and over again, we get people to join in, to ask questions when they don't understand something.
Conversation is different. You get expressions, you understand better in French les nuances in a language.
Coming to work at ITER is like coming to visit all the countries in the world. The countries in the world have come to visit me. It's a very easy way to travel, and it might be called lunches in English, but of course the ideas that are being expressed are coming from Chinese, from Japanese, from all the different nationalities who are sitting around the table. So I'm learning new things.
Although what is happening at ITER represents the cutting edge of the world's technology, the concept of fusion was actually first realized a century ago, when, in 1920, British astrophysicist Arthur Eddington suggested that stars draw their apparent endless energy from the fusion of hydrogen into helium. In 1934, New Zealand-born physicist Ernest Rutherford, known for his work splitting the atom, managed to achieve fusion in a now famous experiment that identified the potential of deuterium and tritium.
So if you look throughout the history of fusion, fusion has gone through ups and downs. For example, back when the scientists were first looking up at the sun to understand what the sun is and how does it work, there was a huge enthusiasm to be able to master the reaction of the sun. And soon we realized it was a complicated thing. And this has then sequenced to the 1950s, where we came up with this idea of magnetic confinement. And then there was an enthusiasm, and then it's dropped down again.
Once it's perfected, fusion power will give us an unlimited supply of energy.
If we learn to perfect it. But even the most optimistic scientists think that fusion power may not be developed for 50 years, if then, if ever.
By the early 1960s, the fusion research community was in the doldrums. Many initially promising experimental paths had all failed to produce useful results, and political will and support was beginning to wane. But in 1968, something remarkable happened.
The Russian scientists came up with a major breakthrough, and that major breakthrough was the tokamak.
It was at least 10 times what the best machines anywhere else in the world had been able to do. The results were so good that some dismissed them as down to faulty measurements. So what they did was to invite a team of scientists from the UK, who had been developing their own reactor on very similar lines, to independently test the Russian machine.
At that point, not only did the tokamak give birth on an international scale, but that was also the birthplace of an open collaboration. So this was really the hot point of the Cold War. And Russia said, hey, look, we have this result. And all the world flocked to Russia. And then from there, the Russians shared their experience. And at that time, it was complete open and positive exchange. And that's what I think is cool about fusion, is fusion has no boundaries.
One other event, which was a landmark moment in the history of fusion, occurred in November 1985. When in the midst of Cold War tensions, President Gorbachev and President Reagan met for the first time at the famous Geneva summit.
These two sat down and wanted to find out a way to move forward in a peaceful way. And one of the outcomes was that Gorbachev and Reagan decided, let's join forces and build a joint machine, an international machine that would try to solve fusion. And thanks to that, today we have ITER being built.
Over the years, that international cooperation has been well and truly put to the test. Nowhere more so than in the building of the vacuum vessel, the very heart of the reactor, which will enclose the burning plasma. It's made from 9 gigantic segments, 5 made in Europe and 4 in Korea, incorporating a double layer of nuclear-grade steel. Each segment weighs 500 tons, over twice the weight of a boxcar locomotive. Despite their enormous size, they require millimeter precision. With so many companies involved in numerous different countries, every aspect of ITER is an extraordinary exercise in planning and logistics. As almost half of all the components for the reactor are being provided by Europe, it was decided to set up a separate organization called Fusion for Energy, to enable a myriad of European companies to work together and find new production processes to create this one-of-a-kind engineering marvel.
Some of the things I like about fusion is that they're just mind-boggling. And even though I do this for a day-to-day type event, I heat plasmas, it's to some degree inconceivable to me that I can heat a plasma to 150 million degrees.
Although the main body of plasma created in this fusion process is contained within a magnetic cage, neutrons are also released. On the one hand, that's good, because they provide the heat energy. But as their name suggests, they are neutrally charged, so they can't be controlled by a magnet. They move at incredible speed. If nothing blocked their path, they would reach the moon in just 8 seconds. When the neutrons hit the wall of the vessel that surrounds the plasma, they can, over time, cause damage. So whilst building work began in France, it was vital that the team working with the jet reactor in the UK came up with a solution.
This is a photo of the inside of JET, about half size. It's twice this size in reality. And it gives you a good idea of what the inner skin of the reactor looks like. For a long time, all of these tiles on the inside of the reactor were made out of carbon. And the reason we did that is because carbon's a very forgiving material. And when you're an experimental device and you want to push the limits of the experimental device, we could overheat the carbon and the tile didn't change shape. The problem with carbon is that it reacts with the hydrogen. It reacts with the deuterium and tritium is in the plasma, that are your fuel. And it reacts in such a way that it locks the fuel up inside the machine. So what do? You change from carbon to metals.
But getting metals into the reactor to test proved a challenge in itself. Because of low-level radioactivity and the need to keep impurities out, they needed to find a way of working inside the chamber without actually entering.
We're in the JET remote handling control room. This is where we maintain the inside of the reactor vessel. We need it because JET is the only machine in the world that uses the fusion fuels, and therefore it has an activation level inside the machine. So when we talk about you're not allowed to go in there, we're talking about radiation levels that are comparable to what you get from walking around for a year. We're trying not to increase the dose of any of our workers significantly above what the background level is. So like a lot of JET, it's all one-off, it's all been built from the ground up. It's taken 20, 30 years to develop this. It started off with technology that came to us from the high-energy physics community, but it has been developed all out of recognition since then. It's incredibly sensitive. It's possible to do things like start to screw in a volt, feel that it's cross-threaded, back it out again, and put it in straight with this tool. It's possible to feel the edge of a piece of paper, that sort of a step. It's very, very sensitive. Everything is rehearsed in our training facility before it's done inside the machine, and it takes months, if not years, to get to the point where you're a fully trained operator on this system.
This highly precise remote handling system meant they were able to remove and analyze samples from the wall of the chamber no bigger than the point of a pin. After much research and testing, they decided on two metals. The first was beryllium, a very light, unreactive metal used to make, among other things, missiles and aircraft.
Beryllium we use in the main chamber because it's next to the high-temperature fusion plasma. Here, we have the 200 million degrees that you need in order to make fusion happen. As powerful as the magnets are in JET that make this cage that keeps the plasma away from the wall, there's always some leakage. And in a tokamak, in JET, we arrange it so that those losses are diverted down to the bottom of the machine.
Here they use tungsten, which, although slightly more prone to react with hydrogen than beryllium, is one of the toughest metals found on Earth.
In the bottom of the machine, the plasma is much colder. It's only 20 or 30,000 degrees. At those sorts of temperatures, with a high melting point material like tungsten, the plasma can touch the wall.
But changing the lining of the vacuum chamber was no small feat. It meant replacing 4,000 tiles, all of which had to be done remotely. The knowledge gained here at Culham has meant that ITER's remote handling simulator has already been built, meaning trained operators will be ready to go as soon as the reactor is fully assembled. Whilst a huge international effort has been going into building a viable energy-producing tokamak by 2025, there are some in the scientific community who believe we should be pursuing a very different route to fusion. In the 1970s, scientists began experimenting with powerful laser beams to heat a sphere containing hydrogen isotopes, to the point where they would implode with enough force for the hydrogen atoms to fuse.
Here's how it works. An ultra-high-powered laser would fire its light beam at a very small pellet dropped into a target chamber. The pellet would be hit from all sides at the same time, its outer layers vaporizing away, the inner core compressed.
This implosion mimics the huge gravitational force that stars use to create, then contain, the fusion process. It's called inertial confinement fusion. But as with everything to do with fusion, life is never that simple. To momentarily implode hydrogen pellets smaller than a sugar cube requires a laser that is 10 stories high and covers an area twice the size of a football pitch. But the inertial confinement story doesn't end there.
So this is a pistol shrimp, and if you're wondering what this has got to do with fusion power, then that's a very good question.
Nicholas is co-founder of a company called First Light Fusion, who was inspired by a small but remarkable crustacean to look at creating inertial confinement fusion in a way that requires only a tiny fraction of the energy of a giant laser. The pistol shrimp snaps its claws so quickly that it creates a sonic shockwave that can stun or even kill its prey. The speed of its snapping jaws creates a gas bubble that collapses in on itself. As this cavity implodes, the air and vapor inside is heated to such an extent that a plasma is momentarily formed, which has been estimated to have a temperature close to that found on the surface of the sun. It's the only known example in nature of internally confined plasma other than a supernova.
With the shrimp, the plasma is whatever happens to be in the bubble, which is a bit of gas and a bit of water vapor and so on. For us, to make this into a scheme for fusion power, inside the bubble you put deuterium and tritium, and it's the deuterium and tritium which are getting heated by that collapse process. Instead of clicking the claw, what we use is a high-velocity projectile. So this is what our targets look like now. So this is our replacement for the bubble that the shrimp creates. If you look at one of our simulations, this is the simplest possible one, with just one bubble by itself. You can see there's a huge amount happening. But one of the key things is the pressure wave, which is moving in. When it hits the top of the bubble, it causes it to turn inside out, and it forms a jet, which moves across the bubble and then hits the back wall of the bubble. The key thing is that actually that jet moves faster than the projectile. It compresses the fuel inside, the deuterium and tritium, and for a tiny fraction of a second it gets to enormous temperature and density, and it will give a pulse of energy out, a pulse of neutrons out. And each one of these targets will release about the same amount of energy as an entire barrel of oil. And that's how the power plant works, is you put one of these into the power plant, you hit it with the projectile, it releases some energy, you have to capture that energy, and then you have to do it again at some frequency, and that's how you get power out.
Having originally experimented with a gas gun, they found that although they could launch a small projectile at 15,000 miles per hour, it just wasn't fast enough. So they moved on to electromagnetic launchers, which use a huge pulse of energy.
Okay, so this is machine 3, our latest pulse power machine, an electromagnetic launcher. In here we've got 192 capacitors. We charge these up to 100,000 volts. And when they're fully charged, we've got 2.5 megajoules of stored electrical energy.
Which means that this machine has the ability to generate an incredible 14 million amps.
Okay, so it's much easier to get a feel for M3 from up here. We've got the 6 limbs, the 6 banks of capacitors arranged around the outside. When the switch is closed, the current flows down each of these limbs and into the center section. So what you can see here is our vacuum chamber, which is just being assembled. It'll have a lid on it, it'll be sealed, and within that is where our load section goes, where all of this power converges. The load is this circular disc here, where the 14 million amps flowing, they converge in this very centerpiece down the middle here. And in there, There's a very small disc which bursts free. It's machined out of one piece. It's right at the bottom of that sort of chimney section, and that's where the current's flowing, and that piece breaks free, and it flies up that chimney, and that's where it hits our target. So the real challenge is getting the energy into the load as quickly as possible. And to achieve that, we have to close the switches in tens of nanoseconds. That's billionths of a second. Once the switches are closed, and we're discharging the whole machine in 1.5 microseconds, and for that instant, the power in the load is greater than the US national grid. So the projectile can reach speeds up to 20 kilometers per second. And to give you an idea of that, it would be London to New York in about 4 minutes. So it's really moving when it gets to the top of that chimney. A pilot will pass out at around 9G. This is experiencing around 1 billion G.
But as impressive as the projectile mechanism is, the main focus of the team is to create the optimum interior of the small target. This means experimenting with different sizes and numbers of bubbles, which all interact with each other to amplify the shockwave.
The benefits of our approach is the rest of the power plant is so much simpler. It's nearly all existing technology, in fact. So if we can make this work, we have a much simpler pathway to fusion power, which is what matters.
Okay, short time. Check set voltage and current. Siren on. Dumps open. HV on.
Beginning charge to ±70 kV. 10 kV.
Diagnostics.
60 kV. Approaching full charge.
HV off. Send trigger.
As the lid of the vacuum vessel is removed, the evidence of the huge, albeit fleeting, creation of energy is immediately apparent. But while this machine is a good way of testing individual fuel cells, a working power plant would need to provide a constant stream of such energy pulses.
Our current thinking for, let's say, repeating this process of impact between projectile and target is to inject the target potentially only by gravity down a tube, and then that target would be chased by a projectile which has much higher velocity. For the projectile, the target is as if it was stationary, in fact. You need to imagine this event being repeated every 20, 30, 40 seconds. And basically, every time there is an event, you get a burst of energy. In order to convert fusion energy into heat, you need a device called a blanket. In our reactor concept, those blankets are fall-in curtains of liquid lithium, which serve multiple purposes, in fact. One is to convert the fusion energy into heat, which can then spin a turbine and generate electricity. But the reason why it's lithium is also because that allows us to breed or to produce the tritium that we actually then have to feed back in the process because it's one of our components of the fuel.
Fusion can be done, and it will be done, and it can be done in time to solve climate change. Right, if we're going to get to net zero in 2050, we need 10 plants on the grid in 2040. To get 10 plants on the grid in 2040, we need 1 plant in 2030. To get 1 plant in 2030, we need to prove the physics works in the 2020s, in this decade. And we can get there. Even the big mainstream projects can get there. ITER is going to have first plasma in 2025. But in principle, they can do it, they can get there. And that's the timetable we have to hit. It is possible, it's going to happen.
Back at ITER, after a decade in the making, the large components are due to start arriving from all over the world. But in all the years of planning, there is one thing that even the brightest minds in the business have not anticipated: a world in lockdown. For Alain Beculé, the head of engineering and the man charged with overseeing the assembly process, it was just one more challenge in a long line of challenges.
So how did ITER cope with the COVID-19? It's really a moment when we have discovered new or other ways of working, and we very likely will take lessons out of that. So the number of people working on the construction side was cut by 1/3, but we still could carry on the main activities. On the engineering, corporate, science and operations side, everybody went home, everybody worked from home, and people carried on designing and working from home. In a sense, we are used to it because the ITER organization is spread around the world, so we are used to work remotely. And as I said, we are now taking lessons also out of that and trying to create what we are calling now the new normal, because in a way, it works.
If visible proof were needed that progress is being made, it doesn't come much bigger than this. The 3 massive sections that make up the cryostat have been completed. The base alone weighs 1,250 tons. But building a reactor out of such huge sections created yet another technical challenge. How do you first move them, then assemble them in their final resting place in the reactor hall? This unprecedented problem required an unprecedented solution. A vast assembly hall has been created next to the reactor building. Within it, 2 newly installed cranes, able to lift 1,500 tons, will carefully carry each unique and precious component to what is known as the tokamak pit. It's a hugely symbolic moment, as it represents the start of the assembly process.
It's really the precision that we want to have all along the movement. So this element, this huge plate, is moving centimeter per centimeter.
It is crucial that the cryostat base is positioned in exactly the right place. Around it, the rest of the reactor components will be assembled. Components which have been a decade in the making. Components which have been designed to be millimeter perfect in order to fit together. No ifs, no buts. It has to be right.
If we are not sure that it's perfect, we have to come back immediately to this imperfection. Otherwise, if we let imperfections develop, then at the end of the day, for sure, it doesn't work. It is the Pisa Tower, if you want. If you don't pay attention, at the end of the day, you have this. Okay, we want something that is perfect.
Having arrived over the tokamak pit, it now needs to be lowered. It's a painstaking process which moves at an almost glacial speed.
And there are controls all the time. It's real-time control, the position, the locations, and so on. If you are in front of it, you almost don't see it moving. It's controlled millimeter per millimeter. This is really impressive.
But with so much of the huge reactor being constructed off-site, there are still over 200 giant shipments, some of which weigh over 400 tons, that need to make the 100-kilometer journey from the port. However, when they did the calculations, they realized there was no route that could cope with the massive dimensions. And so roads have been widened, intersections changed, and even part of a cliff removed.
To the question, are you relieved when it comes? Of course, but more than relieved, we are so happy.
Now the assembly can begin in earnest. Although it will be 5 years before the giant reactor fires up, to the thousands of scientists and engineers around the world who have been working on fusion for over half a century, this is acknowledged as a landmark in the future of fusion energy.
I think, for me, this is the end of a very long road. It's quite a matter of some pride that we actually managed to do this, and it's all come together and it's here.
But for COVID-19, today would have seen a celebration attended by the world's leaders and huge international press coverage. But in some ways, the small gathering of scientists who have made it here today is far more apt. They represent people that have devoted a lifetime in pursuit of this goal, and they are keenly aware that they are passing the fusion mantle to the next generation.
Well, yes, I'd like to manage to keep going for another 5 years and actually turn it on to check that it works.
It's an enormous challenge for our generation, for the generations to come, and I hope that people will be excited about what we're doing here at ITER, support it, but also get involved themselves and go into the engineering disciplines, go into the scientific disciplines that will be necessary for that reality to be true for the planet.
I do feel like I've added a contribution along with thousands of scientists before me and thousands of scientists in the future, that we together have provided an energy source.
Why do I do it? I do it because I look at my kids and I honestly am convinced that this is the way. This is the way to solve the future problems we have. In addition to renewables, yes, it's a combined energy mix, but there's nothing else on the table that offers this amount of energy benefit for such a low impact on the environment.
I met some of the engineers working on the Apollo project when I was a kid, and I thought, wow, it must be really cool to work on the Apollo project to put the man on the moon. It's the same thing. To me, it's just the ability to say, I helped build this thing. I helped humanity overcome our energy crisis. And that just seems like, wow, that is really cool.